Okay, so today we are going to talk about the position analysis of a slider crank. So this will be a 4-bar link, there's 4 links in this analysis, but instead of 4 pin joints, we have a full slider. So we can say that when we analyze this, we're going to say that the slider is perpendicular to the x-axis. And let's say that we're analyzing an engine piston or something like that, where it's not necessarily horizontal. So long as we define the x-axis as the direction that's perpendicular to our slider, this analysis will work. And we can say that we have link A, which goes along vector R1 at angle theta 2. Then R2 has a magnitude of B and an angle of theta 3. R3 is 90 degrees with respect to the horizontal, so it's completely vertical, and it has a length C. And R1 is completely horizontal and has length D. So if we want to draw our vector loop, we can add up the different components and then set them equal to 0 because we end up where we start. And we have A cosine theta 2, A sine theta 2, plus B cosine theta 3, and then y direction B sine theta 3, C minus 0C minus D0 gives us 0, 0. So we have these two equations. And if we go ahead and see what are the things we know. So as always, we're going to say we know theta 2. We also will know our A length and our B length and our C length. The only thing that changes would be the length C and the angle theta 3. And so theta 2 is an input, and so we can put that in and find everything else out. So we have 2 equations, 2 unknowns. It should be feasible to solve for them. And if we go through and solve for them, we can see that theta 3 is equal to the inverse sine of C minus A sine theta 2 divided by B. And D is equal to A cosine theta 2 plus B cosine theta 3, which is nice and convenient. We can just take that D to the other side. So now let's go ahead and set up MATLAB. Oh, one more thing. Before we set up MATLAB, we could talk about some of the geometric constraints. So we have our vector loop, and if we want to see the maximum distance D that we can have, then that would be setting R1 collinear with R2, so that they're going in the same exact direction. And that'll be the farthest that we can have. That D max, using Pythagorean's theorem, would be equal to the square root of A plus B squared, as one cohesive unit, minus C squared. Then for D min, we have that R1 is in the same direction as negative R2, so they're going opposite directions. And now we have D min can be, not D min, D minimum can be set, and that would be equal to B minus A squared minus C squared. Now, this gives us some orientation or some guidance for A squared, or for C with respect to A and B. So C has to be smaller than the summation of A and B in order for us to physically be able to build the link. Because if we have that they're set equal, then you don't really have much of a moving link, but you could have a coupler R1 going entirely vertical connected to R2 going entirely vertical going to R3. And you could physically build that, but it wouldn't slide at all. There would be no motion. Similarly, if we have that first criteria is met, but the second one is not, then we would have C, the magnitude of C plus A, because if C goes below the horizontal, that's fine. They have to be less than or equal to B. If not, the crank cannot have a full rotation. The book has a great picture. I'll see if I could put that on the canvas with here. And that just means that it's essentially the crank can't have a full rotation. It's a non-Grashof type link. So let's go through, and Grashof's not the correct word, but we get the idea. So now we want to create MATLAB for the slider. So first we have all of our front material. So you might want to have your file name. You want to give a little synopsis of what your file would do, and then you would say who's working on it, write the author's names. And then you could set some values for A, B, and C, and that would be based off of your design. Then you'd want to make room for D, your position of C, your position of B. You'd want to define your number n for the number of calcs, and then you create your little for loop that can find those calculations, and you could plot that. We can also, in that for loop, put the positions for xc, xb, and that way we can plot the linkage itself. But when we're creating MATLAB, we might want to come up, script out a little bit of what you want to do, and write it down before you start going into MATLAB, because that way you can look at everything in its whole, in its entirety, and figure out how to go through this. So I'd say go through the MATLAB on Canvas, make sure it makes sense to you, but in our for loop, theta2, we will define if it can create a full crank, then we'll have it go from 0 to 2 pi. If it can't, then we need to set the boundaries of that. Theta 3 can be found if we have theta 2, and D can be found once we have theta 2 and theta 3. So I'll link the MATLAB, and I'll say that's the end of this video.